Hello everyone, I am Alexander Gomo and I'm here to present you growing synthetic data through differentially private Vine copulas. Let us swiftly begin talking about synthetic data. Companies are catching up on the hype, for the good and for the bad. But here's the thing, we need a way to privately share data. Can synthetic data be the answer? Is it the answer? Well, we might answer that question, but it for sure seems to be an adequate way to provide private yet realistic data. There's also a huge literature on the subject with few methods ensuring differential privacy by design. Here's three. There's DP copula, which is a copula-based generation. They use differential private histograms as well as differential private estimation of a Gaussian copula to estimate the trend distribution. Major drawback from this model is that they simplify the dependent structure to a Gaussian model. The spread-based as a statistical-based model, well, more precisely a Bayesian network-based method. The major drawback from this one is that the greedy construction of the Bayesian network is time-consuming, which makes it impractical for high-dimensional data. There's also DPGAN, which is which is for generating synthetic data with a differential private GAN frameworks, but GANs can be tricky to play with. So here we come in with copula Shirley for copula-based generation of synthetic differentially private data framework. It is based on Vine copulas to be able to model complex distributions, and its main strength is simple to use and deploy, flexible and private. Simple due to the nature of the mathematical objects upon which it is based, mainly density functions and histograms. Flexible due to the highly customizable framework centered around copulas. And private, as it is differentially private by design and coupled with a privacy test for membership inference. First thing first, let's talk about copulas. They date back to 1959 they were formalized in 1959 by Sklar. In the last decade, copulas have experienced a significant growth in many domains. In a nutshell, a copula is a multivariate cumulative density function on the unit cube, modeling the dependent structure with many families to pick from for the best fit. Coupled with the marginal densities, or simply marginals, the model is complete. Here are some key concepts centered around copulas. Pseudo-observations are ranked normalized data. Marginals are the univariate densities, and the PIT, which is a probability integral transform, enables us to transform data to pseudo-observation. The whole process goes like that. With data that we have here, we estimate the marginals given here. From these marginals, we can compute cumulative density functions, which are then applied to the data itself to produce pseudo observation. This is the PIT. So the applying CDF to the data itself, this is the PIT. So with the pseudo observation, we can then fit copulas from many families. Like here is the independent copula. Vine copulas were introduced in the early 2000s to refine the modeling capacities of copulas. The principle behind it is simple: decomposing the multivariate function of copula into multiple bivariate copulas. A vine is a set of nested connected trees such that the edges of a tree correspond to the vertices of the following tree. So here are two representations of a vine. When I say the edge of a tree corresponds to the vertex of the following tree, this is what we mean. So edge, vertex, edge, vertex. Here's a more clear example. Down here we have the variables. This is the copula that models the two variables. This copula is the copula that modelizes the two copulas here. This one modelizes these two, and so on. The construction of a vine is non-trivial. The current state-of-the-art technique for vine selection vines uses a top-down greedy algorithm known as Desmond's algorithm. The technique is based on the hypothesis that the top of the vine is more important in modeling the data than the lower branches, as they contain raw information about correlation between attributes. Desmond's algorithm can be summarized in three steps. Choose the optimal tree that maximizes the sum of correlation coefficients between variables. Choose the optimal copula family for each pair of attributes. The pair are imposed by the tree. That minimizes the information loss. Then construct all the trees for the following level from the previous optimal tree. And then go back to step 1 until no tree can be constructed. Now for copula Shirley, here's a high-level overview. 4 inputs, so the training dataset, the privacy budget, the number of records to generate, and the encoding method. The encoding method here is quite important. This is the next slide. 3 steps: preprocessing, vine selection, and data generation. Quite simple indeed. Why data encoding? Well, copulas mostly use rank correlation for modeling dependencies, so we need an encoding technique for handling categorical values. We studied 4 possible encoding techniques. Of course, there are more available out there. The first one is a common trick, that is to view categorical data simply as discrete data in which the order is chosen arbitrarily, for example, alphabetical order. This is known as the ordinal encoding. Another technique is the use of dummy variables in which categorical values are transformed into binary indicator variables. This is known as one-hot encoding. We also studied 2 supervised encoding techniques, which are the weight of evidence and the general linear mixed model encoding. Supervised because they both need a reference attribute called a predictor to encode the categorical attributes in a way that maximizes the correlation between the pair. First step is preprocessing. So this is quite a crucial step because it includes the encoding of categorical value. We need to split the dataset for learning the CDFs in the selecting of a Vine model in a differentially private way. Since our framework needs 2 sequential training processes, that is the differential private cumulative density functions and the Vine coupler model, we rely more on the parallel composition of the differential privacy and splitting the input dataset into 2 distinct subsets instead of using the sequential composition of the differential privacy and splitting the global budget epsilon. The third step is computing the cumulative density functions. We do that by the way of histograms, by the way of differentially private histograms to estimate the probability density functions. Then a simple normalized cumulative sum over the pin counts provide a good enough estimation of CDFs. With the CDFs, we can now compute the pseudo observations because, as I repeat, couplers can only model uniform standard marginals, well, pseudo observations, but easily enough the probability integral transform does that exact thing for us. The second step is the Vine selection. We propose the use of Desmond's algorithm on the noisy pseudo observations, as it is the state of the art, and this is where we kind of set apart in the literature, because the existing previous works at the intersection of differential privacy and copulas are restricted to Gaussian copulas, as it is easier to build Gaussian copulas in a differentially private manner. It's quite simple, in fact. The use of Vine copulas in the same way is a bit more complex, as there are multiple sequential estimation, which would result in an overall huge injection of noise due to differential privacy. In contrast, coupler surely reduces the complexity by computing the dependencies on the noisy pseudo observations rather than computing DP parameters, and thus enabling the use of Vine couplers in a private manner. Differential privacy is guaranteed as both the preprocessing and the Vine selection only interacts with the data through DP mechanism. The last step is data generation. It is the simplest one. So first is sampling observations from the vine using inverse probability integral transform to map back the data to its original domain and then reversing the encoding if necessary. For the experimental evaluation, here's the setting. We used 3 datasets, adult, Compass, and Texas Hospital. The later one we sampled down to 150,000 records and 17 attributes due to computation limitation. We used a k-fold cross-validation with 5-fold. For each fold, the models generated the same number of records as the training set. We compared also 5 values of epsilon, the DP budget. So 0, 0.01, 0.11, and 8. 0 here means that the differential privacy is disabled. We compared 3 differentially private algorithms, DP histograms, which is simply computing the DP histograms and then sampling from them, PrivBase and DP coupler that we introduced a bit before. We used a few metrics, so to test the statistical similarity, we used the Kolmogorov mean of distance and the mean correlation coefficient difference. We also used the Matthews correlation coefficient on the 2 classification task, which is the binary and multi-label classification, when we used the root mean square error on a linear regression task. We also tested 4 parameters, so the splitting ratios between learning the CDFs and learning the Vine. We also tested the encoding techniques, some DP mechanism, and the truncation level of a Vine, because you can stop the Disman algorithm at any level. We also evaluated the privacy through a membership inference attack. We used the Monte Carlo membership inference attack introduced in 2019 at PETS. The main strength of this attack is non-parametric in its agnostic model. The privacy score is can be briefly summarized as the ratio of training records successfully distinguished from control records. 1 would be perfect distinguishability and 0.5 would be indistinguishability. The best configuration that we observed for the splitting ratio is 50-50. Well, there was no clear consensus, so we kind of used 50-50 here. The encoding method for categorical attributes, we used the weight of evidence encoder. The differential privacy mechanism, we used the geometric mechanism, as it is a refined version of the Laplace mechanism for discrete histogram computation, which is, that's why it performed a bit more better in that way. And we also view that the truncation level of the Vine coupler model doesn't impact much of. There was not a huge gain in utility past the second level. The overall result is that our method is second to PrivBase on ML tasks. It has the highest distribution similarity. It's comparable to DB histogram in that fact, and there's a better protection on large data sets. And it's also quite faster. For the classification, the dashed lines are the baseline, which is computed on the right dataset. PrivBase outperforms our method, but our method seems to be a bit more stable in that way. If you check the width of the stats. Then for the regression and correlation, the root mean square error, the lower the better, and the same is for the mean correlation delta. Here, PrivBase also outperforms a bit coupler surely, but still copulas is more stable overall in that matter. As for the distribution, similarity, and privacy, copulas is often offers the most similar distributions, uh, way ahead of priv-base in that matter. And for the privacy, here the closer to 0.5 is the better. So for Texas, which is the biggest dataset, copulas provided the better protection. Same here for adult, it did not outperform priv-base on Compass though. We also did an additional analysis on multivariate correlation, which is a small synthetic dataset composed of 5,000 records and 6 attributes with various correlation coefficients between the attributes to study the model strength in capturing the dependent structure in the data. The data was created so that some attributes are highly positively correlated when the values of the first attribute is below 0, and only slightly negatively correlated when the values are above 0. We can see here, so below 0 is highly positive, and above 0 is negatively and slightly. Both copulas and priv-base performed quite well for the four highly correlated and the slightly correlated, but priv-base outperform copulas when it comes to splitted correlations and the data. Here copulas kind of interpolates a bit more than priv-base. So here's a bit of a summary result. Copulas displays the highest statistical similarity between the raw and synthesized data. Priv-base is often the winner in terms of classification task, with copulas often being a close second. dpcopula and dphistogram display the worst utility, so copulas can be seen as an upgrade of those two. One thing to mention is copulas is much faster than priv-base, and we were also made aware prior to recording the video that the implementation of priv-base we used violates the formal assumption of its TP guarantees, so we will not discuss the priv-base versus copulas protection here. So that's it. Here's some perspectives on the future work. Thank you for your time. I've been Alexandre Rogemont. You've been you.